Assalamu alaikum. My name is Tayyib Hussain and I am from UT Texla. Today we will learn about digital filters in part A of the video, and then in part B of the video we will learn about the moving averaging filters. First of all, what are digital filters and what are their importance in DSP? Basically, the digital filters are being used for the two purposes, that is of the suppression of the signal and restoration of the signal. The suppression of the signal will be held when the signal is being distorted, and the restoration of the signal is being when its shape changes almost, and then we have to restore the signal. Their examples are electrocardiology and digital crossover audio system. These are the two basic examples of the digital filters that are commonly used in the market. Beside this, restoration of the image is the term similar with the restoration of the signal in the same way, and we can observe it in time domain. And there are three kinds of responses. First of all, it is impulse response in the digital signal, and second one is step response, and third one is frequency response. After all, the value used to measure the level of intensity of the signal's intensity has been measured by this dB scale of logarithm, and this formula can be represented by giving the power, and this formula dB is giving now and the intensity of the signal. And then we will move towards step response. The step response is very usual and very important because it determines slow or fast the signals of strength, overshoot, and linear and non-linear. If a system has to be determined by these kinds of responses, they can be easily determined. Now moving towards the ripples produced by the high transistors, we have to basically minus or delete the low pass filter from the impulse to give our high pass filter. So if we apply fast Fourier transform on the signal, and there are two methods to solve it. Number one is spectral inversion, and number two is spectral reversal. Now this is a step response signal, and when it is multiplied with the low pass filter, and we will get this desired signals by having, always we will start with the low pass filter and then we will get our desired signal. That is it from our first lecture of part A in this week. And now moving towards the second part, that is moving average filters. Some most of the simplest filter, you can see that this is h of n is 1 1 1 1. This is the most simplest filter. That's why it is being usually used in the market, and the dealers are being shy to use it. But this is the basic formula for the determining the moving of the average signal. And here you can see the formula of y of I, the output, 1 over m, the value total, and j to 0 summation m minus 1 to x, and this formula x I plus j, and then you can get the series of the response. And there are two kinds of samples that will be found. The one is specific sample like this x of into 80, and other is delay, because there is a minus sign, and minus 80 means that there is delay in the sample. So this again we will moving with the one example, that if we have a 11 point moving average noise can be minimizes from the signal, and if we have a 51 point moving signal, we will lose the signal version as we minimize the noise too, but we will lose the version. So in designing, the most important factor in the filter is that it will cover both the smoothness and step response in balance. That's why. And here is some filters in the frequency domain, and you can see here this is some kind of the filter, and then we have to apply input signal x of n on it, and after applying we will convolve it. After convolving we will get the following result. There is a result after convolving the following values, and then we divide with 3 because it is an input, and then we will get the following result, that is these number of the values. And now we will then converting into the frequency domain, that we will apply fast Fourier transform on it, and then the signal is first of all convert into 2 points FFT, and then 4 points, and then at the last 8 points FFT, and then we will get the original signal back like in the time domain. And the next thing is alternate when we required best attenuation result, then the Gaussian formula will be used, and then the Blackman is used for the fast roll off. And the last important thing is that recursive implementation, that is very important, in which there are two kinds. We have finite impulse response and infinite response, and the behavior of the recursive manner we will consider it in this example, that this is the formula for the recursion. Y of n is basically sigma k minus infinity to n to x of n, and you can see here is the basically the formula and these two terms will add up and they give the result. Now you can see this is the input signal 0 0 0 1 2 3 1 2 0 1 1 and 2, and what is this recursion back, that is will be number will be added in the previous value. So 0 0 0 will remain same, 1 will come as it is, and 1 plus 2 will become 3, and then 3 plus 3 6, and then 6 plus 1 7, then means next value will carry on, and after the um, adding up all the values it will remain the highest value, that is at last it will be 11, 11 plus 2 13, and then input values becomes end, and that's why 13 will continue. That's it from this lecture, and we learned it about digital filters and moving average filters. See you to next time in inshallah. Allah Hafiz.